Hey everyone, welcome back. This is episode 1, and the question we're looking at today is why do computers use binary? So let's break it down from first principles. The real question is why ones and zeros specifically, right? Let's think about the last time we booked a movie ticket on an app like Book My Show. We typed on a seat, the app confirmed it, and we got a QR code. You do know that all of that is represented as binary within your phone or in the database, right? Including the seat number, the show time, the QR code that was generated in itself. It is not because zeros and ones are elegant or efficient. It is something much, much more basic. So let's try and understand the constraint that exists in modern systems. There's an important thing about the physical world, right? It is messy. So when we send an electrical signal through a wire, that signal does not arrive perfectly. The voltage that you send is not the voltage that you receive. Wires that are used to transfer these signals have resistance. Connections that are established have noise. Nearby electronics radiate interference and your phone gets warm. You know what? The heat that is produced by your phone or a computer as it operates also changes how components behave. And it's no surprise that power supply that we get at our homes also fluctuates. Every single wire inside a computer is a noisy, imperfect channel. This is an oscilloscope. I've just tried to represent how a square wave signal can look at its recipient side. If you notice all of the noise, that is coming because of heat, interference, resistance, and supply drift. So imagine you're designing a chip and you want to represent the number 7. If you use a decimal system, you would need the wire to carry one of 10 distinct voltage levels. Say 0 volt means 0, 0.5 volts means 1, 1 volt means 2, and so on, right? If you can see, I've denoted all of these voltages here. And so 4.5 volt will denote a 9. If there is noise and you had sent a signal, let's say we're talking about 2.5, but the voltage that was received was 2.7, would you consider that as a 5 or a 6? Think about it for a moment. Effectively, if the noise on the wire is plus or minus 0.3 volts, then 2.7 volts could have started as a 2.4, which is 5, or as 3, which is 6. You genuinely cannot tell, and this is not a software bug that you and I can fix. This is physics. Basically, you want to increase the margin that is available between the states that voltages are going to represent. The more levels that you try to cram into the wire, the less the margin that you will have between them. And that introduces the chance for noise to creep in. As more states are represented by this wire, there is going to be more noise that will affect the final values. And this is the fundamental constraint. The physical world is analog and noisy, but we do need reliable, unambiguous answers. So while physics is limiting us from being able to send perfect signals, we want systems that can be perfectly decoded from. And so that is why we ended up doing something which was the obvious fix. Why not use more voltages? Hey, why don't we have 10 voltages and then dedicate a voltage each to all of these numbers? And this is giving a headroom of a full voltage when the noise or margin for error is 0.3 volts. So for example, we use 0 volts for 0, 1 volt for 1, and so on. Now a signal that will arrive at 2.7 volts is clearly a 2 because the nearest boundary is at 2.5 volts and you have half a volt of margin. This works in theory, no doubt, but here is what it leads to. Inside of a chip, what happens is a modern processor having billions of transistors, signals are constantly being copied, amplified, and routed through layers of logic. If every signal needs a 10 volt range to stay reliable, your chip needs a higher power supply. Fair enough? Which means more heat, and that means more noise. Which basically then means you need even more margin. And so now you're chasing your own tail. I hope that's clear. So you're just wasting a lot of power to keep these levels apart, As you keep increasing voltage, you get more heat, and so the error margin increases. And so this is where it really falls apart. Inside of a chip, signals do not just travel from one point to another, right? They pass through gates, and gates have their own imperfections. If you notice, every gate which is supposed to output exactly 3 volts might actually output 2.8 volts. It could be because of manufacturing variations or because of the various interferences that we discussed. The next gate receives 2.8, adds its own noise, and passes on 2.6. After a few layers of logic, your clean 3-volt signal has drifted to 2.4, and now it's indistinguishable from a 2. So what originally started as 3 has become 2. If you notice in the diagram, that is exactly where it falls apart. Now think of signal degradation and how it can compound. With 10 levels, every gate needs to be precise enough to preserve the distinction between adjacent levels. With billions of gates operating billions of times per second, the probability of a wrong answer becomes unacceptable. You would definitely need to build error correction into every single gate, which would make the chip slower, larger, and even more power hungry. And this is why the decimal approach does not scale. Make sense? More power, more heat, error correction in every gate, all of these are not things that we want to deal with. So then, what is the real design? So instead of 10 levels, we know that we use 2, call them 0 and 1. In hardware, 0 is a voltage near 0, say anything below 0.8 volts, and 1 is a voltage near the supply. So let's say anything above 2 volts. And the gap between 0.8 and 2 is called a dead zone. If a signal lands in the dead zone, the system is broken and you fix the hardware itself. But in normal operation, every signal is clearly in one zone or the other. And because there is a huge margin, you know that the chances of signals drifting even further apart are low. One of the key insights is not just that 2 levels are easier to distinguish. It is that we can build gates that restore signals. A gate can look at its input, decide if it is a 0 or a 1, and output a clean and fresh version. If the input is 0.2 volts, it knows that this is closer to 0, and I know that my output can be a 0 volt itself. If the input is close to 2 volts, you know that the output is closer to 1, and you want to output a full volts all over again. Because every gate regenerates the signal, noise stops compounding and it gets erased at every step. Moving on, let's try to group these bits together. And there's a reason for this. One bit is a 0 or a 1, not very useful on its own, but 8 bits together can represent up to 256 distinct values. Like from 0 8 times to 1 8 times. We call that group of 8 bits a byte. And with a byte, you can represent any ASCII character, any number from 0 to 255, any of the hundreds of colors in a palette. And the beauty is that this group is pure abstraction. The hardware does not have to know it is storing a letter or a number. It just sees 8 wires, each carrying 0 or a 1. The meaning is assigned by the layer above it, which is the abstraction layer. And this is the first great abstraction built in computing. We trade the richness of analog signals for the reliability of 2 states, and we make up for the loss by grouping bits together. So binary is not in that sense a limitation. It's a design choice that we've made to make sure everything else is possible. But that comes with some trade-offs. And let's take a look at what this costs us. What we have gained is reliability as discussed. A binary signal can travel through billions of gates, be stored, retrieved, copied, transmitted, and still arrive correctly. Every digital system on Earth, from your phone to a satellite, depends on this. We also gain simplicity in hardware design. A gate that distinguishes 2 levels is very easy to build and fast to switch and cheap to manufacture. But then what have we sacrificed? We have sacrificed density. A single wire carrying 10 levels could obviously hold so much more information than a wire that is carrying only 2 levels of information. To represent the number 255, a decimal system will need only 1 wire. A binary system needs 8 wires, 1 per bit. And we use more wires, more transistors to compensate for this lack of density. But because transistors are cheap and have been getting cheaper, this trade has been worth it for decades. One more thing that we've sacrificed is called directness. I mean, you and I think in terms of decimals. When you see the price of a movie ticket, you would rather want to read it as a 250, not as 111111010, right? Every interaction between humans and computers involves translation between decimal and binary. It is invisible to most of us, but for programmers, we've dealt with so many of these bugs so many times that by now, yes, this is a sacrifice that we've made to be able to work with systems that are more reliable. So here's the takeaway. Computers use binary not because 2 is a magic number, but because the physical world is noisy and 2 states give us the maximum margin to tell signals apart. Every gate regenerates the signal, erasing noise at every step, and we group bits into bytes to build meaning on top of that reliable foundation. We'll get into that foundation over the course of future videos, but here is something to think about. We said a byte is 8 bits and it can hold 256 values. But who decided that a byte is 8 bits? And what happens when you need to add 2 bytes together? A wire can hold a 0 or a 1, but it cannot add. Something has to do this arithmetic. And so in the next episode, we will open up the machine and see how a computer actually calculates starting from a single wire that can be only on or off. So a zeros and a ones combined together, sent over. How would you end up adding 2 distinct values is what we'll look at in the next episode. I'll see you around.